Good afternoon and welcome to another MBT Fireside Chat. The topics we'll be covering today are some questions on the double slit experiment, some questions on the Monroe Institute, which Tom is going to be involved in next year sometime. Most of our questions are about out-of-body experiences, so that's quite appropriate. Some on NPMR, some on beliefs, and on empathy and empaths. So let's get started with the first question. We recently, Tom, you recently did an interview we called, we recently posted an interview from the Spokane workshop, an excerpt of the double slit experiment, and that's been quite of interest to some people. So the YouTube video that we posted from that workshop is called The Key to Understanding Our Reality. So let's start with a question that Justin had on the double slit experiment. As a thought experiment, if we place a single slit some distance before the double slits and measure the particle as it passes through the single slit, will the given particle be required to act like a particle when it arrives at the double slits?
Well, to answer that question, you'd have to know exactly where that single slit was located. You see, the key here is uncertainty. If the single slit was, and I'll be vague on purpose because it depends on the setup, how big the particle is, all sorts of things, but if that single slit was a long way in front of the double slits, then that single slit wouldn't make any difference whatsoever. Okay? Even though you measured a particle there, there'd be enough distance between that slit and the double slits, you know, the single slit and the double slits that were behind it. There'd be enough distance there that you would, again, gain uncertainty in the particle's position. And as long as the uncertainty in the particle's position then creates a probability distribution about that uncertainty, you know, of where the particle is, and if that uncertainty being captured in the probability distribution covers both the slits. In other words, the probability of where it is pretty much equally likely, could end up at either slit because of the distance between the two. Then the double slit experiment would work with just like it would if you didn't have that single slit up there. Now you've just made your source of the particle the single slit. That's the only thing. That's the only way particles are coming in. Now let's take the other extreme, and we take that single slit and move it right up behind one of the slits, very close. Okay. Now whenever you see a particle going through that single slit, you would indeed have to get a particle going through the slit right behind it. You see. So it depends on where you put it. Those are the two extremes. It's moved far enough away that you create enough uncertainty that you don't know where the particle is anymore. Well, that's just the way the experiment started in the first place, so it has no effect. If you get it up real close, then yes, it does make a big difference. Now, we could put it up very close, but say between the slits, so that the only place that a particle would go, that we measure the particle, and I assume that everything else is walled off. We're not getting particles from multiple sources. We're only getting particles that have come through this single slit. So the single slit is in a wall, and the wall, intercepts all the other particles except what gets through the single slit. Then what would happen if we were close to the double slit, but somewhere in the middle between them, is that we would probably get very, very few particles ever make it through either slit, right? They would probably hit the barrier between the slits, but then we back it out a little bit more, you see, and if we backed it out a little bit more, now the probability of where the particle might be just enough to overlap both slits. And if that was the case, we'd get that same experiment again, but it would probably be with a lower density of particles, because some would fall out there and others would fall in the distance between the slits and therefore never pass through a slit. So then we back it out a little more. So you see, it kind of depends on what you get as to where you place it, how close, and whether it's in line with the center or whether it's off center. That makes the difference. The key here is uncertainty. The reason the double slit works the way it does is that there's uncertainty about where that particle is. And if we don't know where it is, then basically what that means is it could be anywhere. Well, we look at our probability distribution, and if that probability distribution overlaps both slits, then it could go through slit A or it could go through slit B, and now we're back to the same, double slit concept that we had before. If we somehow collimate the particles, so we only know particles are going to be directly aimed at slit 1, now you've put a big bias in your experiment. See, that's not, that would be pretty much like covering over slit 2, and now we just have a single slit, so it's not the same experiment. So it's all about uncertainty and the probability distribution and the symmetry of that probability distribution about the two slits. So we could take our source of the particles that we're shooting at these two slits and move it off center. So it's no longer really centered on the area between the slits, but now it's moved off, say, to the right or to the left. So you would have a higher probability of getting the particle through one slit than you would the other now, because the probability distribution is maybe a little steeper, at the right slit than it would be at the left slit. In which case, you would get a double slit experiment that was not symmetric. Some of the times, you'd have it going through both slits and interfering with each other, but some of the times it wouldn't, and you'd get a slighter diffraction pattern and a much bigger pile when you did do the measurement, behind the one slit that had the bias toward it. So you'd get a kind of an in-between thing. That's, so it's all about that probability distribution and what does that distribution look like. And the probability distribution is a probability of where the particle is. And that's what makes the double slit. We don't really know where there's a particle. Matter of fact, it's not just that there is a hard particle somewhere and we just don't know where. It's that the hard particle doesn't exist except as a probability distribution. You see, we don't want to get trapped in the kind of what our kind of intuition, which is calibrated by this physical reality. We don't want to get into the trap of thinking, well, there's really a single little hard particle out there someplace and we just don't know where it is. That's not the idea. The idea is that particle is just probability right up until the time a measurement's made, and then a random selection from that probability distribution tells you where the particle is. That's, the measurement. The measurement does that. So the particle is probability. But the way that probability distribution exists relative to the slits will change the probability of getting a particular measurement in either slit, or at none of them at all. So that's kind of the general answer. So it could create all kinds of different results depending on where you put it and how you centered it and how far away it was, because it's a matter of probability and uncertainty.
So Tom, would you say there's always been this idea that quantum physics applies to very small things with a large amount of uncertainty? Is that uncertainty really just based on the fact that we can't perceive it unless we measure it? For example, if you shot like the example of a toaster, the hypothetical example where you shoot a toaster through double slits, you'd be able to see the toaster. I mean, I guess would be why it would break down. I'm not sure. You see what I'm? I get hung up on it between the differences.
And as long as you could see the toaster and measure with your eyeballs where the toaster was, that experiment wouldn't work. Okay, and the only reason that it works with particles is we can't see the particles, so we have no idea where they are. Therefore, there is no measurement taken until the actual measurement at a slit. So we don't know where they are before the measurement's taken. Whereas a toaster, if we can look up and see, oh, here's a toaster coming, out of, right field, there's a toaster on its way, and we all can look up and see it. Well, as soon as our eyes see it, that's a measurement. Okay, the measurement's been taken. There it is. We know where it is, and if we know where it is, it's going to crash into whatever's in front of it, just like you would expect anything else to do. It's not going to perform a pattern. But when they talk about the fact that you can scale the double slit experiment up, there's no reason, there's nothing in physics that limits it to small things, you see, and that's because the idea that quantum mechanics is a physics of small things and doesn't apply to big things, that's wrong. Quantum mechanics is quantum mechanics. It applies to all things. But you have to set up now an experiment that's very difficult because the toaster has to be coming from such distances that we no longer know where it is, and it has to be going with such speeds that we no longer, see it. We no longer know, it has to just be a probability function. There is no measurement taken of it. There can be no measurement taken of it until you actually have a device to measure. And the slits couldn't be tiny little slits. Obviously, they got to be slits big enough to pass a toaster, you say. But so experimentally, the idea of using a toaster through the double slit experiments just doesn't work because experimentally, that's just in the too hard to do category. Buckyballs, which are big 60 atom carbon things that look like soccer balls, that's done, but then they're really too small to see. And it's not that hard to lose track of a buckyball. It's really hard to lose track of a toaster. So we can arrange the proper distance between the slits and the proper distance of the source and all that with buckyballs and still get the double slit experiment to work. But we go all the way up to toasters. The physics says it ought to work just the same. But it's just a very hard problem to actually do an experiment, you see, to test that, because now we have a different kind of measurement problem. We measure it all the time, you see, with our eyeballs. We can measure it. We do know where it is. And when that's the case, it's in this physical reality by our measurement, and it'll crash into whatever it crashes into. But if we could arrange an experiment so the probability of where the toaster is was uncertain enough that probability covered two big slits that were big enough for toasters to go through, then it should work the same way. The toasters then should arrange themselves in a diffraction pattern. You see, at least that's the physics. There's nothing in the physics that requires the size to be small. What requires the size to be small is the fact that the reason it works is because of the uncertainty, that you don't know where the particle is. That the particle is not really a particle, it's just a probability distribution until the measurement's made. Well, with toasters, that measurement gets made, unintentionally even, with our eyeballs, it gets made in other ways. So that's how that works. Now, the quantum mechanical ideas, this idea that something is probability until we see it, I think I've mentioned this in one or two of my talks. We can kind of move this up to a grand scale, and then that will get rid of the idea that this is the science of quantum mechanics only applies to little things, or not even the science of quantum mechanics, that this idea about things are probability until the measurement's made, that only is true of small things. It's mostly true of small things. Well, let's put it this way. It's always true of small things that are so small that we can't see them, you see, now because they have a lot of uncertainty. So that's why quantum mechanics tends to be applied to the world of micro, because that's the world in which everything has uncertainty and we don't know where anything is ever until we make the measurement. So it seems to apply there. But the concept is a general concept. And the analogy I make is let's talk about the largest things, which is the science of outer space, if you will, the universe, cosmology. And if we look there, and if we point a telescope suddenly we get a brand new telescope that sees farther and clearer than any telescope has ever seen before, and we point it at some unknown part of the universe that we haven't seen before, and we look, it works exactly the same way as particles going through a double slit. There's some probability of what's going to be out there at this grand scale. No one's ever been able to see it. Even though it's very big, no one's ever been able to see it because of other technical problems. It's not the size that makes it hard to see, being so small, it's that it's so far away is what gives it its uncertainty. We don't know what it is. Nobody's ever seen it. It's too far away for us to have probed and looked at before we got this new instrument. So now we point this new instrument at it, and we look through it, and we take a picture, and it works exactly the same way as a double slit. There may be 1,000 different things that could possibly be there at that point in space, given all the things that we do know, which is a lot about, how things are in outer space. We have looked at a lot of things. So we're not going to get something that's totally inconsistent with what we've already seen. It has to be consistent with what the known facts are. But there may be thousands of things that are consistent with what the known facts are and be in that space. So there's a probability distribution across all those different kinds of 1,000 things that might be there, and some of them being more probable than others. And when you randomly pick, not just among the things, but pick out of the distribution, that's a different thing. When you pick out of the distribution, you will select one, and that's what you get a picture of, the one that's randomly selected among all the possibilities from the distribution. So it works the same way as in the micro scale. And the reason it does is because in both cases we have uncertainty. We don't know what's there, or we don't know where the particle is. And the fact is that reality is probabilistic. Everything is probability until somebody needs it in their data stream, right? Reality is actually individual. We all get a data stream, and a data stream defines our reality to us. So it's all these individual data streams. And if there is no individual that needs that data in their data stream, that individual is just, that object that no individual needs in their data stream is just probability if it's never been here before. If it has been here before, then it has to be consistent with what it was before, you see? So that's the way it works. So there's a class of things on both ends that have a lot of uncertainty about them. And that's the very far away, the very big stuff that's so far away that we've never seen it and don't know what might be there. And the very small, because it's too small for us to, have any of it in our data stream. So that's where it applies mostly. But then there are these odd things that can happen right here on the planet in everyday life. They're not in the very small, they're not in the very large, but there's still uncertainty about them. And that's, when I go through the little thing about the man, walking into the woods, right? If you have somebody who's seen something for the first time, and there's no data in PMR about what's going to be there, then but it sounds like somebody just pulled the plug on the bathtub. Okay, there we go. So then you have a situation where some person is looking or measuring, whether it's measuring with their eyeballs or measuring with an instrument, or whether they've just dug a hole in the ground, where nobody's ever looked what's in that hole before. It doesn't matter. If it's something where there is uncertainty, then we're in the exact same boat here in the normal macro world that's not beyond what we've ever been able to see. Well, it is, but it's not outer space and it's not tiny particles. It's just the regular macro world that we live in every day, but there's uncertainty about some things. And if you're the one that measures that uncertainty for the very first time on this planet, then you will be the one, by your measurement, that takes a pick that's a random, selection from the distribution of things that might be there, and you will get an answer, just like in the double slit. So this uncertainty thing is most obvious in the far reaches of outer space and in the tiny little microparticles, but it's also around us every day. There's all kinds of things we do that might have large uncertainty about them because they've never actually been measured before. They're not part of what's here. Now, if you look at a hole, that's, you dig your own hole and you look at what's in the bottom of it, okay, that may be some uncertainty, but it has to be based on being consistent with what we know about what's liable to be in a hole of that depth and in that location, right? You're not going to dig a hole and look through the other side and see little blue Smurfs, playing in the ground below, because that's not something that's likely to be there. So, but whether or not you find a diamond or whether you find gold, well, that would depend on the probability of diamonds or gold, being at that location. And if that was a 1 in a trillion probability, then you have a 1 in a trillion chance of finding a diamond or a piece of gold there. So what you're what really is probably the highest probability is you're just going to find dirt and rocks, right? And maybe you'd find a dinosaur bone, but that would depend on the probability of, you know, whether there was a dinosaur bone there. Now, sometimes you do get something that's very improbable. It just might be that the probability of a dinosaur bone, let's say, is just 1 in a million because of where you're digging and how deep you are and all the rest of it. Well, that 1 in a million can come up on a random draw. It's not likely to come up. The stuff that's more, you know, more probable, the way distributions work is that when you take a random draw out, what you get is what's most likely to be there. You know, that has the highest probability of coming up. The thing like the dinosaur, 1 in a million dinosaur bones, it's possible you could pull that one out, but it's very unlikely. But sometimes that happens. Sometimes you pull out the dinosaur bone and there it is, and now you've got a dinosaur bone that was only 20 feet under the ground, and it's, you know, in a place where nobody had ever seen dinosaur bones before, and it's just one of those darn anomalies in science and with the world that everybody scratches their head about and says, wow, I wonder, that dinosaur must have been lost, you know, how'd that happen? Well, we do have odd things like that. I mean, we know, you know, as you study science and as you look at things, you know, there's all these kind of anomalies. There's just weird stuff that doesn't quite belong, but there it is. Well, those are things that are not likely, you know, but possible that get pulled out. Well, they're still possible, so it could be there. It just doesn't happen most of the time. Mostly we get pretty much what we expect because we have some idea of what's likely and what's not likely. So that's kind of an overview on how all this works. So this idea that things are probability until the measurement is made is a general concept that covers small things, you know, big things, and in-between size things. It's just the way our world works. And it's also a reason why sometimes some very squirrely things can happen. For instance, in science, we have this thing called tunneling. And they have particles trapped in a well, what they call is in a potential well. That just means there's a force there that keeps all the particles, you know, in a box within a certain position. They're not allowed to get out. If they try to get through this box, then the wall of the box, whether that's a magnetic field or a piece of iron, whatever, keeps them inside. And when we do this with small particles that we can't see, well, now there's a probability distribution that those small particles may be outside of the box. It's only 1 in maybe a billion that it's going to be outside of the box because, after all, it can't get through the wall. But if you have 100 billion particles in there bouncing around, the 1 in a billion, you're going to draw that out once in a while, right? So that means that you'll find that magically, without any reason, a particle that should have been in the box will be found outside of the box. It's called tunneling. You know, and it's a fundamental fact that, you know, that happens. Matter of fact, it's so common that we even make electronic components out of that, you know, out of that fact. The tunneling diode is a standard electronic component that you buy for, you know, 25 cents, you know, at your parts store. It works based on the fact that things tunnel and get to where they're not supposed to be. That's you know, so it just works that way in all parts of our reality because of the nature of the reality. So once you see that it's about uncertainty and taking random draws from probability distributions, and that everything starts as a probability distribution because this is a probabilistic, you know, virtual reality. So being a probability distribution is like the natural, you know, beginning thing. And then we beings here, and it's not just we people, you know, the squirrels too, playing in a tree, you know, they make measurements as well with their eyes and their nose and their other senses. And it works the same for them as well. So it's not just us. It's not that we magic humans are so important that this world, you know, centers around our, you know, our measurements. Every conscious critter out there is making measurements all the time, and they influence what, you know, what's manifested, what they get. And when I say manifested, people are thinking of, oh, you know, the system has to produce a chunk of mass somewhere in the system, you know, now that's a particle. Oh, we got a little chunk of mass that wasn't there before. But what's manifested is basically manifested as data in a data stream to that consciousness. That's the manifesting that's being done. It's not that chunks of mass are being created and thrown into this virtual reality. It's a virtual reality. It's just a computed reality. So what's being manifested, what's being created here is information. You say it's information that's being made, and information now goes to that individual in his data stream. But because that information is here in that individual who's here in this physical reality, then we have to have a consistent physical reality. We can't have somebody, when we do an experiment, it can't come out 6 different ways. It only comes out one way. So you have to have consistency. So what you get manifested in your data stream has to be consistent with what everybody else has gotten manifested in their data streams up to that point, because this is a multiplayer game, and we have to share, our reality. It has to be consistent across not only all the people, but all the squirrels and all the bugs as well. Everything that has an awareness and an ability to make measurements and receive data, then they have, they're part of the game for making this be the way it is. So when we go into that woods and we see things, what we get is modified by what the squirrels got who were in there before us. You see, we may be the first human being to walk into that woods, but if there's squirrels living in that woods, then we have to get something that is consistent with what the squirrels got. Now, squirrels don't see the same world we do. We see a completely different world than they do. But where there's overlap between the squirrel's view and our view, we have to have the same view. So actually, when you walk into a woods, it's not just a blank slate that you could get anything, but there's parts of it that are blank because parts of it aren't in the squirrel's data stream, aren't in any squirrel's data stream, aren't in any bug's data stream. It's what the people see when the people look, and that part you get to freshly make up, if you will. What you see is what's there, and now it's going to be what's there for everyone as long as that data stays here. So that's kind of how it works. We all have to share in this reality, and the bugs and squirrels are part of it as well. They just have a very different viewpoint. So it's not hard for our, but sometimes our viewpoint and their viewpoint needs to overlap. And when it does, then we have constraints on what we're going to measure, because some of it's already here. We can't suddenly have the squirrels living in a tree and we walk into the woods and, we take a random draw and that tree doesn't exist anymore. Now what happened to the squirrels? They're off playing in another dimension. Well, that would require the computer to make more and more dimensions and more worlds just to keep everybody happy so that the squirrels didn't suddenly get evicted. You see, but it doesn't do that. That's very wasteful of computer resources. That's kind of the many worlds theory, that anything changes anywhere. You start another universe. Well, that's kind of ridiculous as far as computer resources go. You don't want to start a new universe because something different happened. You have to have a universe that remains consistent, which puts constraints on the probability distributions that you get to pick from when you make your measurements. And that's why, because that's true, that's why our reality is a shared reality. That's why it's a multiplayer game. What that means is there's consistency between players. See, so that's how that works, and it's a much better computer science solution to deal within those constraints, because those constraints are not that horrible that we can't compute, what everybody sees and keep kind of records of what's going on. That's not that big a deal. It's just a matter of keeping all the data and keeping it consistent. And if you make a mistake and there's an inconsistency, well, there's ways to kind of, erase that, and get around that so that everybody says, gee, that was weird, but I don't know what happened there, and then they move on because the system maybe got caught, in an error, and now it just kind of gets covered up, and people and bugs and squirrels are very quick to forgive and just figure they must have had a lapse, a senior moment, or something happened and it didn't really happen and it was all in their imagination. So the system doesn't have to actually be perfect. It's not that hard to cover a mistake if the system makes one. So it's not it's even easier than it sounds. You know, World of Warcraft can do it. You know, they can have, I don't know, 100,000, you know, players in there all at the same time, and, you know, keep the game consistent for everybody most of the time. You know, and I'm sure if they have errors or something, they, you know, it's not that hard to get by some errors. So it's not as tight a constraint on the system as one might think. Well, I probably told you more than you wanted to know, but anyway, I thought there was a lot of basic ideas there that a lot of people would maybe get something out of.
Yeah, no, thank you. Have you ever, by chance, heard of the game Minecraft? It's kind of the newest thing among kids.
I have heard of it because my grandchildren are addicts, evidently. They play it all the time, up to the limits the parents allow. Right. And I've never played it, and I don't know much about it, other than it is very popular among kids today, yes.
Well, my son plays it a lot, and one thing I noticed about it, which fits in exactly with what you're saying, is that there's no preset map, I guess, from what I understand. It's generated on the fly based on probability. So if you're walking through, I don't know, a desert area, it's calculating what's most probable to be next as you keep walking. And then once it's rendered for you, it maintains historical consistency and stays. But, you know, 100 blocks away where you've never been, it sits in a state of uncertainty, and it hasn't been rendered yet or settled yet. So I thought it was pretty interesting that the game's based on reality.
Yeah, that's the way it really works, right? And that's the most. And the reason that they probably ended up doing it the same way that reality is done isn't because they know how reality is done and they wanted to do it that way. It's because that's the most efficient computer science solution to the problem. You see, you have a whole bunch of players, and you want to make a consistent reality for them, but you don't want to necessarily sit down and draw every blade of grass that's going to be on your map. Well, how do you solve this problem in the most, you know, efficient way for the, for the processing? And they seem to have come to the conclusion that if you just do it on the fly and then maintain consistency, that's the solution. So I'd say that's kind of a, you know, a mark, an example then of how it is that it works this way. You know, well, it's efficient. That's the efficient way to solve the problem, to sit down and actually program in every blade of grass, every tree, everything there ahead of time, and then play to that. That's probably the way World of Warcraft is done. You know, they have to put everything there, but they probably have a huge overhead in maintaining all of that, and they're not as flexible. They can't make stuff up as they go, you know, stuff that fits. They kind of have to stick with what they've already thought up in the past instead of, you know, it's a much more limited way. When you do it on the fly, then even the creator doesn't know, you know, what's going to be created next, because it just happens as it happens. It's not a done deal. And that turns out to be a very efficient process. And that's why the larger consciousness system uses a process like that, not because, you know, it just does that. It just, you know, that was what came up first, but it's obviously over millions of, you know, tries and over lots of evolution, it's settled in on the process that is the most effective and the most efficient to produce the learning lab that we need to, you know, function in. And that's the way it's done. So it doesn't surprise me at all that our you know, computer science folks trying to make virtual realities end up, again, in this fractal process, you know, copying the process that's, you know, that's already there. That's kind of the way it works. Yeah, not surprising, and good to hear, though. It's another, you know, piece of data that falls into the right place, that they should end up doing it that way, because that's the way the fractal works. You know, that's the process that has been evolved to be most effective.
Nice. Thank you for all that, Tom. Donna, I don't want to hog all of Tom's time, so skip my other questions, please, so other people can ask them.
Well, that's all right. We'll go through them. There's all questions with the same theme, so that'll probably fit right in. Tom, I don't know if you've had a chance to see some of the comments on the same video we were talking about in the beginning, the key to understanding our reality. But there's a comment on your explanation of the delayed choice experiment. The comment kind of questions your explanation on it. And the comment says, if you make a measurement and then erase it, then the measurement was never made. So clearly, it can't be the measurement that collapses the wave function. Rather, it is something beyond measurement. The collapse of the wave function occurs when a knower with a certain level of knowledge has enough information to make a determination. When all the info is erased, then there's not enough information and the wave function occurs. I think we're left with either the many worlds interpretation, which would not explain the probable nature of the electron, or it is consciousness with a certain level of information, which would also explain why people, animals, insects, and plants experience different levels of reality, and why people with various levels of understanding experience a reality limited by that level of understanding. Could you comment on that?
Sure, I agree with the commenter. Right up until some of his conclusions, he's right. When you're in an erasure experiment, what happens is that you had information that would have specified what the result would be. Okay, you measured which particle went through which slit. So you have what's called the which way data, and that's which particle went which way. They just, in science, you kind of shorten that and call it the which way data. So you have the which way data, and that means the experiment should turn out in a certain way. But before that which way data is ever looked at, and before the results of the experiment are ever looked at, you get rid of the which way data. That gets erased. This is an erasure experiment. And it's called a delayed erasure because you get rid of it after the results have presumably already been collected. In other words, you already have results on the screen. Nobody's looked at them, and nobody's looked at the which way data, but the results are presumably on the screen before you erase the data. You see, so that's what a delayed erasure experiment means. And what they have found, and there's lots of those experiments have been done, and I talk about one of them particularly in the Calgary workshop. I give the citation and the name of the article and who did it and that kind of stuff. So if people are interested, you can go to Calgary and see a good paper on a delayed erasure experiment. And the key here is that we suppose that that result is already done. In other words, we look at time and we say, well, the experiment's over. We've collected the result on the film or in the computer, and it's there. We haven't looked at it yet, and we've collected the data from the slits, the which way data, and we haven't looked at that yet. Okay, so it should be done. If we throw the data away, if we erase the which way data without looking at it, and we still haven't looked at the result data either, now what happens is you go back to the diffraction pattern on your result that wouldn't have been there had you kept that which way data. You would have got two dots. But because you throw the which way data away, now you're going to get a diffraction. That's what happens in the real world. That's what the scientists get when they do the experiment. Okay, that's what happens in a delayed erasure experiment. After they throw the data away, they get a diffraction pattern again because that slip data isn't there anymore, and that's what gets everybody in a whip. Well, the fact is you haven't made what was collected change. We just assume that data that was collected is in a certain configuration because we gathered that which way data. But nobody's looked at it yet. So the measurement's never been made. What's on that final photographic plate, if we're going to say that's where the screen is on a photographic plate, if what's on that photographic plate's never been looked at, you see, it's still probability because that's the way the world works. Everything is probability until the measurement's made. So there's a certain probability of that being both a diffraction pattern or two spots. As long as you have that which way data here and it's available for you to look at, then when you do that random draw, you're going to find out that there's a 1 probability behind 2 spots and a 0 probability behind a diffraction pattern, because that which way data is here and available. Once you throw that which way data away, the probability changes. Now there's no data here to confirm how that comes out. Well, you can say, well, there was data, but nobody ever saw it. What if that data, what if the machine messed up and that data is, isn't really there? Or there? I mean, there's all kinds of possibilities of something that nobody ever looked at, you say. So now you go and make that draw on the screen, which is this photographic plate, to see what's there. And there is no information here that would require it to be 2 spots anymore. Well, you get the default answer. The default answer is, a diffraction pattern, because there's no information here to say differently. That's how the erasure, the delayed erasure, it works. And basically what he's saying in his comment is true, and I agree with it. And it is true that the probable, what is it called, the many worlds doesn't answer that question, because the many worlds tries to keep everything materialistic. We have another material universe, in which it's this way, and a material universe which is some other way, and it completely misses the idea that this is a probabilistic reality. It tries to keep it a deterministic reality. So it's gone down a deterministic path with its multi-universes, and that's wrong. It doesn't work that way. And I agree with him there entirely. But it's not at the end that it's about the consciousness is looking at it. I mean, it is in a way, because it takes a consciousness to make a measurement, right? If there's nothing here that's consciousness, if there are no data streams, then there is no game. There's nothing here. So yes, it takes a consciousness to have a data stream, and we're talking about the information in the data stream. So in that indirect way, you can say that it's a consciousness that makes the difference. It is in an indirect way. But directly, what directly makes the difference isn't whether or not the consciousness believes there's 2 dots or a diffraction pattern, or whether the consciousness, has any opinion about that or not. It's not what the consciousness is aware of. It's just the information. When the information's here, that would contradict, if it got a diffraction pattern, and you then looked, and then you had this which way data, and you looked at it, and you had all the data which the particles went through. Now there's a conflict in the reality. You've got data here saying that the results should be A and the results B. That's a problem. You see, you can't let that happen. You can't let the reality give you 2 facts that are incompatible with each other. That is not acceptable. So the reality doesn't do that. Because you don't have the data here, then you still have the probability. It's our assumption that the plate, the photographic plate's already been exposed. It's done. It can't be changed. Therefore, if you erase the data, the which way data, you can't, you're still going to get those 2 dots, damn it, because, the plate has been exposed, and that's just the way it is, and nothing else could change. And the fact that now you get a diffraction pattern after you erased it after the plate was exposed, that just isn't right. Well, sorry, but, the experiments say that is the way it works. That you do get the diffraction pattern even when you erase the data after the fact. And the reason is that that plate has not yet been exposed. That plate is just a probability of where those patterns, where those particles are going to end up. That's just probable. That you don't get an actual fact of what's on that photographic plate until you look at it. And when you do, you get a random draw from the possibilities, and if there is no data to say otherwise, you get a diffraction pattern. If there is data, you get the 2 spots. In other words, it's a probability of 1 or 0, or a 0 or a 1, based on the experiment. And that probability can change based on whether or not you erase the data. So it's the people who have this materialistic belief that feel that photographic plate with either the 2 dots or the diffraction pattern on it is a done deal, can't be changed, because they believe in materialism. And anything else just is impossible. This is not, world is not run by, materialism. It's not a deterministic materialist world. It's a probability run world. And the probability isn't computed until after the measurement's made, and the measurement isn't made until you look at that photographic plate and see what's on it. And what's on it will reflect the probability distribution at the time you made the measurement. And when you throw that data, the which way data out, you modify that probability distribution so that when you look at the plate, you get a modified result, because now you're making a random draw from a modified probability distribution. That's how it works. So you have to realize that nothing really exists physically in this world. Okay? Nothing is really in this world until that measurement is made, until that brings it here. So that plate, okay, our deterministic materialist theory says that plate is exposed either with a diffraction pattern or with two dots on it. That's the materialistic, viewpoint. That's the deterministic viewpoint. So it just blows our mind when we erase the data after the fact and we don't get the two dots. Well, the failure is, of course, the fact that it's not a materialistic and it's not a deterministic reality. And that's what the scientists have a really hard time coming around to see. That's why quantum mechanics is this impossible science that nobody will ever understand, shut up and calculate kind of thing. So what they need to do is get a bigger picture of what's going on here and realize that it's a probabilistic reality, not a deterministic reality. And the probability can change. And when the probability changes, the result changes. Now, once you looked at that data, if you took that which way data and looked at it, all right, now it's here. It's not just a probability of being here. It's not a probability. All right, the device should have taken the measurement. Once we look at it, the measurement's been taken, and here's the result. Now you've got to get two spots on the plate, because otherwise it would be inconsistent, you see? So that's why it's key that you don't look at that which way data and you don't look at that thing, because that keeps both of those in probability. Well, now you erase the data. Well, there's no probability how the data came out anymore. You can't say, because there is no data, it's gone. Now there's a probability of how the plate that has the results on comes out. That probability is still there, and it's a diffraction pattern, because that's what we call the default value. If there's not anything that forces it to be different, that's the default value. And we don't have the data, we don't have the which way data that forces it to be different, so we get the default value, which is the diffraction pattern. So Donna, the comment was made was correct. That is it. And you can say, and people do say, that consciousness, it's the knowledge the consciousness has. Well, if that's the same as saying it's the information, then I agree with that. But there's other ways, you can do this experiment and you don't have to have any consciousness around, and people will say this. It says, oh, well, what if this experiment was done robotically? It was a machine. There is no consciousness involved in it. It's just some random time. The machine turns on, does the experiment, takes the data and clicks it off, and nobody even knows that the experiment's been done. At least they're not sure of it, because it just happens in a dark cave someplace. It happens once every 100 years. And a random number turns it on and the experiment's done. There's no consciousness involved in it. How would it work? Well, it works exactly the same way. In other words, it's not really consciousness driving it as is information. So that's why I say, yes, consciousness is the key element, but indirectly. Measurement is a key element, but indirectly. See, if nobody ever looks at that plate, it remains in a probable state, right? It remains in a probable state, so nobody looks at the plate. And it's not until somebody looks at it that the plate actually gets either a diffraction pattern or two dots on it. That is just in time. They appear on that plate just as the measurement's made, you see. It's not like they've been there all along. They get rendered to the data stream of the consciousness who's looking at the plate when he looks at it. Up until that time, it's not been rendered to any consciousness anywhere. It's just probability, and it stays probability. So that's kind of the guts of how this thing works. So yes, it is consciousness, and the consciousness is in this case, what's taking the data, it's doing the measurement. So you can say it's measurement, you can say it's consciousness, but fundamentally, the best way to say is that it's information is the key. And the information has to stay consistent. So I don't disagree with his comment. It was a good comment, and I can see his point in claiming that it's consciousness that's behind it. It really is. So is measurement behind it, but information is more fundamentally really what's going on there.